We are Group 15 and our project is an Internet of Things or IoT smart doggy door. While the budget for this project was a concern, our goal was to focus on a system that had many features. We wanted the system to be easy to use such that after installation the user can start using the door right away with as little hassle as possible. Due to the system's reliance on software, it is easy to modify or even add additional features for future updates. These features could include changes to either the firmware or on the mobile application itself. Another objective was to provide a way that the user could actually control the system remotely by adding an interface that most people have quick and easy access to. A goal that was important for us was to make collars to be as cheap as possible. Many animal collars can be expensive and tend to break with little use. However, we want our system to work easily, not only with multiple animals, but without cost being a concern to the consumer as well. The door will be powered from an AC power source, such as plugging the system into the wall. However, despite power loss, we want our system to still operate. Therefore, the system must be able to continue running with the assistance of an external battery for an additional period of time. Dogs are very capable of learning patterns, therefore, when the dog approaches the door, either from the inside or the outside, we want to provide an auditory cue that will notify the dog if it can successfully pass through the door. If the cue does not play, then it is presumed that the dog cannot pass through. For our system to support a variety of animal sizes, we required the inner part of the door, where the door flap is located, to be a 1/4 inch wide, 12 inches long, and 19 inches high. This will allow for small, medium, and even some large-sized dogs to pass through. To ensure that the system is compact, some technologies had to be disregarded. So even though the door could have been implemented in other ways, it would have been constructed at the expense of doubling the height or length of the current dimensions. While the length and height are only slightly larger than the flap dimensions, the width is substantially larger to ensure that all components could fit in the door. The flap must be able to withstand a force of 63 Newton per millimeter squared, so it would not only be secure, but it would also be durable as well. When the dog approaches the door to go either inside or outside, the collar must be read by the system from up to a meter away. The time at which the tag is read, the database must be queried, and the door must be unlocked in under 5 seconds. The infrared sensors, which will activate the camera and detect dog movement, must be able to sense up to 1.5 meters. To prevent the door flap from swinging loosely, it must be locked no more than 4 inches from its default closed position. The buzzer must also be loud enough for both humans and animals to hear, but not loud enough to cause damage. Lastly, the external battery must be able to power the system for an additional hour if the power goes out.
For our project, our group strived for our IoT smart doggy door to be easy to use and to be reliable, while also making the door as secure as possible. To achieve this, our group had to make some compromises, which consist of the cost to create the product as well as the aesthetics of the doggy door. While the cost of production being high is a concern, this can cause the overall product to be higher in quality and accuracy.
Our plan of approach for this project was to break up all the required components to help compartmentalize our goals and objectives. Breaking up the project allowed us to easily direct our attention to individual tasks, rather than tackling the project as a whole. This allowed for clear and defined tasks to be created, as well as having the work distributed evenly. Because we knew that both the mechanical and electrical aspects would take a lot of time, both in precise measurements and acquiring components, we wanted to focus on those two parts first. For the mechanical aspect, the door had to be carefully constructed so that it could be installed easily and operated smoothly. For the electrical aspect of the project, due to the extended lead times when ordering components, we made sure to focus on our PCB right away so orders for parts could be placed as soon as possible. Providing ourselves with this cushion allows us to test our electrical components and place any additional orders. For the software, we had to focus on setting up the back end first, which is like the glue to the system that holds the other parts together. This allowed us to test our embedded software on the Raspberry Pi and our software on the mobile application throughout its development lifecycle.
This is our hardware block diagram. For our project, we have a transmitter and receiver that will be communicating to a system controller that contains a camera, Wi-Fi, and a means of storage. From there, appropriate communication will be made to a buzzer to indicate status, some type of actuation to facilitate the locking and unlocking of the door, as well as a motion sensor that will be included for detecting the presence of a dog. All of this will be powered by an AC wall adapter with an external battery backup in the event of a power outage. There's also a switching module that will initiate the change of power. Each member was assigned primaries along with secondaries.
Here we have the software diagram for our project. Our software setup begins with a user creating an account on the mobile app. Once they've done this, they can go ahead and register their door using the serial number found on the physical door itself. After adding the door, they can add animals that will interact with the door, along with sets of permissions for each individual animal. As can be seen in our diagram, these things all happen in an order on the app, but every step of the way is being recorded by the database. The workload split was decided in a way that both the front end and back end are worked on individually, while having just enough crossover to ensure that both ends are communicating without issues.
This is the pinout configuration for the Raspberry Pi. The motion sensors and the solenoids will be controlled by a few of the many GPIO pins. To control the sound level of the buzzer, the connected pin must be capable of pulse width modulation, or PWM. Both the TX and RX pins used for UART communication, however, must utilize the two pins shown. The camera will be connected to the camera port on the board via a ribbon cable. Lastly, the board can be powered through specific pins or through a micro USB connection.
For our design, we chose the power supply unit to be our PCB, an AC to DC or DC to DC converter. In order to design a PSU, we first needed to establish what topology we wanted to use. We looked at 3 different controller topologies: flyback, LLC, and PFC. There were certain trade-offs that needed to be made in order to find the best fitting design, making the balance between simplicity and efficiency difficult to find. LLC controllers had many advantages. Reduced electromagnetic interference, zero voltage switching, and zero current switching allowed for this topology to have a very high efficiency. However, the complexity mixed with the extremely high efficiency deemed this controller to be ultimately excessive for our design. Power factor correction controllers had a simplistic design, which offered an affordable PCB, but its small range of input voltages as well as its large and bulky design outweighed the simplicity. Flyback controllers therefore posed the best compromise between its advantages and disadvantages, with its simplistic design achieving acceptable efficiency from mutually coupled inductors. In order to create a design to power our project, we needed to consider the power requirements from each device. Our system has 2 voltage rails, 12 volts and 5 volts. The 12-volt rail will be powering the solenoids facilitating the locking mechanism. The 5-volt rail will be powering the rest of the project hardware. Regarding the PCB design, there was a choice between the AC to DC converter and the DC to DC converter. Ultimately, the AC to DC converter posed an interesting and involved design, allowing us to demonstrate a more impressive PCB than the DC to DC converter. Therefore, a 12 to 5 volt module was purchased for our DC to DC. All currents on this diagram are the maximum ratings, ensuring that our design would be able to supply the power required. Here's the PCB design for the AC to 12 volt DC converter. It is a flyback controller with quasi-resonance to increase the efficiency. On the left is the AC input, and on the right is the 12 volt DC output. There is a mutually coupled inductor, as discussed in the flyback table in the previous slide, next to the rectifier, a transformer, and a PWM. The power supply for the project is meant to switch between a wall adapter and a battery bank in the case of a power outage. The power bank that we chose as our backup was a rechargeable 12-volt lithium-ion battery pack with 3000 milliamps per hour. The battery has a 12-volt 3-amp barrel jack output, as well as a 5-volt 2-amp USB output. For our application, we will be using the barrel jack. In order to switch the source of power between the battery bank and the wall adapter, the switching module will output the voltage of input 1 by default. Once the voltage drops below a certain level, input 2 will then be switched on.
Much of the door is constructed using 8 inches by 3/4 inches wood planks. This consists of the outer walls, the floor, the ceiling, as well as the box on top, which will house the hardware components. The hardware housing box has not been added to the door yet, and therefore is not shown in the picture. The inner walls of the doggy door is made up of 1/4-inch wooden sheets and has a gap in between the larger wood planks to house the locking mechanism. Additional wood was placed in between the 2 types of wood to close off the gap between them to protect the locking mechanism from weather and being tampered with. The door flap is made of a polycarbonate sheet and was chosen because it's lightweight, has an impact-resistant surface, is shatter-resistant, and has UV protection for long-term weathering. The locking mechanism consists of 3 pieces that were designed using AutoCAD and then 3D printed. It also contains 4 solenoids that will be used to unlock the door. These 3 pieces consist of 4 locking pins, 2 knobs that are attached to the end of the door flap, and 2 shafts that house the pins. Each pin has a slant on it. that faces outward on each side. This allows the knob to push up the pin, and once this happens, it will be stopped by the next pin and be locked in between the two pins. A solenoid will be attached to each pin, which will allow the pin to be pushed up to allow the dog to exit through the door. This process is triggered by the dog's tag being read by the RFID reader. The locking pins are also set up to only allow the door to work in one direction at any given time. This prevents the dog from exiting through the door and other animals coming in right after. While researching different methods to lock and unlock the doggy door, a few different things were considered. One of them was the 3D printed locking mechanism, as well as the solenoids that our group decided to use for the final prototype. The other considered was a linear actuator, which would be placed above the door and would be used to open the door vertically. We decided not to use this approach because it was costly and the movement speed was only 4.5 millimeters per second. The other device considered was an electromagnet, but this was not chosen since it could interfere with the RFID reader and antenna.
Knowing that we would be capturing images while recording sensor data, while also recording data from the reader, and then communicating everything to the internet, we knew we needed something that could handle everything we were going to throw at it. The first decision to be made was between a microcontroller and a microprocessor, and if we quickly glance at this first table on the left, we see that going with a microprocessor, even if it's the least powerful of the bunch, would still be heaps above the microcontroller alternative. And the operating system with Python support is a plus on top of all of that. Moving on to the second table, here we put the option we were already considering against its two polar opposites. The Pico was very quickly ruled out for its underwhelming power. The Pi 4, while appealing, was more expensive and might have been beginning to reach unnecessary levels of power. IoT projects utilize a database to store all information that will be accessed by users. With a good database setup, we'd be able to easily offer customer support and be able to send out over-the-air software updates to have the project evolve over time. In contrast to storing everything locally only, users can access their system through the mobile app from wherever they are and make whatever changes they like as long as they have an internet connection on their phone. With Firebase, the decision we went with, we can give our users real-time updates to whatever changes they are making while also having everything being watched and noted if the systems go offline. For our project, we wanted to have some sort of motion sensor for security purposes. You never know when some random animal might go up to your door on the outside and be trying to find a way in. Passive infrared sensors were selected for our project because of the fact that sometimes inanimate objects might be placed by the door and we do not want to send out a signal when such is the case. The sensor picks up motion and alerts the camera when it knows that it is a moving, living thing. But at the same time, it will know not to alert the camera if the reader picked up a tag at the same time motion was detected, because that would just be one of your animals registered on the door. In the case that an animal sticks its head through the door but doesn't commit to going outside, we plan on using data pulled from a sensor on the inside to keep an accurate representation of whether the animal is currently inside or outside. With the range, good field of view, small form factor, and low price, the decision that we went with was a no-brainer. As mentioned in the previous slide, our camera will work in conjunction with the motion sensor. Once again, for security purposes, we want to be able to capture an image of what might be outside your doggy door. Images are taken when the motion sensor detects a living creature, and then they are sent to the database and therefore the user's mobile app. When deciding on which camera to go with, the options we were looking at weren't too different from one another. The one we ended up with was cheaper while also having a good angle of view. The low image quality was not of our concern as we aren't using the camera for our user to have new pictures to post on Instagram.
To create the mobile application, we had several options to choose from, such as using Java, Kotlin, Flutter, Swift, and more. We decided to end up going with using the React Native command line interface as our choice. Not only have we had previous experience with React Native, the documentation was also well written, and both Android and Apple are easily supported. Therefore, we did not have to create an app for each operating system. To help with the development process, we used Android Studio to emulate the app on the computer. This allowed for us to view our changes live and make the adjustments quickly. The purpose of the application is to allow the user to interface with the door and to control it remotely. When the user first opens the app, they are prompted to either log in or to register an account. When you register an account, you need to provide a valid email, password, and the serial number of your door. The serial number would actually be given to the user if this was a product they could actually buy. The reason the serial number is required is because this will allow the door and the mobile application to be linked together. Without this, the door would not be able to understand who has access to the door and would not be able to query the user's information. After the user is logged in, all the dogs connected with the system and registered account will automatically be loaded. If no dogs are registered, the home screen will be empty. When an animal is added to the system, the list will update in real time and display the EPC of the collar. The user can then press on the three dots of the animal's card to display the name and the breed of the animal or delete the animal instead. If the user presses on the card itself, this is where they have the ability to change the permissions for each animal registered. For example, a permission may permit one animal to enter or to exit while another animal cannot. Additionally, if it is raining, you can set the permission for one or more dogs to not be allowed outside or even inside if they are already outside and are wet. One of the more unique permissions we have is to set a curfew for each animal. With a curfew, you can set a time frame at which the animal can use the door. For example, if you do not want your animal to go outside at nighttime or while you are away at the store, you can set the curfew accordingly to deny the animal permission. At any point, however, this can be changed due to the remote nature of this application. Also, from the front page, you can access all the images taken by the system within the last 24 hours. This will not only let you see which animals are at the door, but this will also provide an additional layer of security from intruders.
We decided to choose RFID as our wireless technology as opposed to Bluetooth, GPS, and ultrasonic sensing. This is because RFID has fast read rates, consistent communication, and can allow for callers without batteries. RFID offers 3 different operating frequency bands: low frequency, high frequency, and ultra high frequency. Low frequencies are capable of reading from distances of up to 10 centimeters. High frequencies are capable of reading up to 100 centimeters, and ultra high frequencies can read up to 30 meters or more. Low frequency has the advantage of its low susceptibility to electromagnetic disturbance, but unfortunately it has slow processing data as well as too short of a read range for our application. High frequency transmits information faster with low EM interference as well, but still its read range is too short. Therefore, UHF was the frequency range we settled on. However, we needed to be careful with its interference susceptibility. Luckily, we are enclosing our reader in a wooden design, which does not pose any issues. Next, the type of tag needed to be discussed. Active and passive are the 2 main types of tags, where active tags initiate communication between itself and other devices, requiring a battery to be powered. Because of this tag tends to be more expensive, but they do have longer read distances for the same reason. Passive tags, on the other hand, do not initiate communication, but rather wait for incoming signals, requiring no internal source of power. Due to the cheaper price, no battery, and sufficient read range for our application, we decided to utilize passive tags. The tags must adhere to the ISO 18060 protocol standard. Within the standard, there are 6 classes. Class 0 is a read-only passive UHF protocol. Having the tag as read-only prevents the ability to add additional information that can assist with animal-to-owner identification. Class 1 is a write-once, read-many UHF or HF protocol, which is perfect for our design, considering we only need to write once and it falls within our frequency range. Class 2 has an indefinite read-write operation with passive tags, but we only need to write once, making this class unnecessary. Class 3 is read-write operations for devices with various sensors such as temperature and pressure. This was definitely unnecessary, considering we aren't even measuring any of these phenomena. Class 4 has an integrated transmitter, where active tags communicate with other receivers. However, due to the nature of our application, Class 4 is unnecessary. Class 5 is practically the same story, with active tags being able to power other devices. Ultimately, Class 1 was the category that our project fell under. For our reader and antenna, there were some important parameters we needed to consider. For the reader, it needed to support an external antenna operating at UHF and was budget friendly. The only reader we found that fits that description was the M6E Nano. For the antenna, we know that we needed circular polarization, which allows for the antenna to read tags at any orientation. We needed a beam width of around 120 degrees in order to have an appropriate reading area. The read distance we wanted was over 1 meter, but this variable was flexible where the power delivered to the antenna could be lessened in order to achieve a lower read distance. And as far as the cost goes, of course, as low as possible. The frequency range we established earlier was UHF, and the chart shows a few antennas we considered. The Time7 slimline antenna seemed to be the best fit, seeing as its beam width was the closest to what we were aiming for. This is our proposed budget. We knew that the RFID components were going to be the most expensive components, making up for the majority of our expenses. Other components like the sensors, cameras, and battery adds up over time. We estimate around $600, but realistically, it will likely be more.
Here we have our team's division of work. Logan and I were in charge of a lot of the software side of things, with storage, Wi-Fi, database, and so on. Jordan was mainly responsible for the construction of the door and designing and building the locking mechanism. Hunter was responsible for the RFID research as well as designing and constructing the PCB and PSU.
The research, PCB design, and parts acquisition for this project are almost done. We have a bit of progress to make on the software, testing the hardware, and designing the enclosure of the door. All in all, we are about 65% done with this project.
The next step for our project is to integrate the hardware components together, place the hardware on the door, test the PBC and switching module, and to read the Raspberry Pi from the database by next Friday. The week after that, we would like to integrate the camera and RFID reader. The following week, we would like to have the Raspberry Pi communicating with the mobile app through the database.